everyone, and today Nicholas here, joined by Noam Leiter, who Noam is an interesting individual. Let me quickly introduce him for you. So Noam is the CEO and co-founder of Lulav Space, an Israeli startup providing vision-based solutions for space robotics. Noam holds a PhD in Aerospace Engineering, and he took part in development of the Beresheet lunar lander, which we're also going to discuss, obviously. So, and some of the topics we're going to revolve around today is obviously space robotics, commercial landers, on-orbit servicing, and how Lulav Space just plays part in that very nicely. So, hi again, Noam, and it's a pleasure having you.
Hi, Nicholas.
Perfect, wonderful. Okay, so let us dive right into it. So maybe, Noam, you can just give us first a little background into yourself. So how you started, what's your, we know your academic background, you have aerospace engineering. How did that decision happen? And then at what point did Lulav Space emerge into equation? So, yep.
Yeah, so I started my studies in aerospace engineering at the Technion in Haifa, Israel. Mm-hmm. I can't specifically recall why I chose aerospace engineering and not mechanical engineering, but I was looking into studying engineering, and very quickly was fascinated by the studies and more into space than to aerospace. That's where my studies took me, and after finishing my master's degree, I started to work at SpaceAL. SpaceAL is an Israeli non-profit organization developing lunar landers. Quite an exceptional team, and they developed the Beresheet 1 lunar lander for during the previous decade, actually. And I worked there for 5 years as a guidance, navigation, and control engineer. We were quite successful in reaching lunar orbit, and that was, I think, quite a unique mission, the first non-profit or even the first commercial non-government mission to the moon.
That's interesting because I never knew about it personally. So, and I'm sure a lot of people did not. So, that was which year, Noam? Which year?
Yeah, so we launched in 2019.
Okay.
And we also crashed in 2019, just 4 years ago, in April 2019.
Yeah, so you just happened to beat again the iSpace, right? Which was the first commercial just now that happened, by the way, also crashed into the lunar surface.
Yeah, so we know iSpace way back when we were all part of the Google Lunar X Prize competition.
Okay.
So there were perhaps 30 teams from all across the world that participate in the Google Lunar X Prize competition. And all those teams were trying to reach the moon and win the prize. Actually, none of those teams, except of our team in SpaceAL, launched as part of that competition. And it took other teams a few years, teams such as Robotics and Intuitive Machines, to be ready to launch, and they're all launching this year. So iSpace just launched last year and crashed a few days ago. Robotics, Intuitive Machines, they will all launch this year and hopefully succeed. And SpaceAL, it's an exciting non-governmental race to the moon, and bringing small companies, small entities to try and reach the lunar surface, hopefully soft landings this time. And it's quite a challenging mission, and it's not easy not because it's more complex than Earth robotics. It's just much more difficult to validate before you fly, and you don't, and the cost of trying is so expensive.
So what is currently the cost per kilogram to the moon, to the surface now?
So the launch itself could cost between $20 to $30 million. A mission is typically $100 million to bring a few dozens of payload kilograms to the lunar surface. It's $1 to $1.5 million per kilogram to bring to the moon of payload.
Mhm.
Quite a lot, but dramatically less than
Yeah.
in the last 50 years.
Mhm.
Now, after my part in the Beresheet 1 mission ended in 2019, I returned to complete my PhD, and I was thinking, like many others on the SpaceL team, what could we have done better? Not only because we crashed due to some technical issues and not good enough level of validation. I
Mhm.
think the iSpace team these days are going through a similar sequence of
Mhm.
they went through a quite similar sequence of event. Maybe they had some faulty sensors, maybe they had some software issues.
Mhm.
If you don't, if you're not 100% ready for lunar landing,
Yeah.
you'll probably fail, and it's very difficult to get to 100% level of validation.
Mhm.
And well, after being part of a lunar mission and a lunar crash, it makes you think about how you can do things better.
Mhm.
It shakes you a bit. You work a few years on a mission and you think you're like the best in the world, and
Mhm.
well, maybe in the world but not on the moon, and you
I mean, still you reached it. You know, that's a very huge step, right? And I personally never knew about that mission, and it's awesome to learn about it. So, you mentioned it was a nonprofit team, right? So it was not
yeah.
nonprofit organization that was doing all this. So, who was the main like financial contributor again to that mission? As we're talking about those prices, so was it from the government? Was it like
No,
private
most
investors?
private donators, they just put the money for an educational mission.
Okay.
SpaceL's mission, and the following missions, the Beresheet 2, are
Mhm.
all intended to promote science, math, physics, the love of space, and to creating such a mini Apollo effect to bring
Mhm.
people to study more and to try to
Mhm.
do more in space. And that was successful, and it continues. This educational work continues now towards the next mission. And
Mhm.
but I'm part of Lulav Space, and our story is commercial.
Mhm.
So uh, with the understanding that it's very difficult to perform a lunar landing, and more generally doing successful space robotics. Lunar landing is just an example of an autonomous robotic space mission or application,
Mhm.
and shouldn't be so difficult. It shouldn't be different than doing Earth robotics. We're all flying drones and have really advanced robots on Earth, and the reason we are successful with Earth robotics and advancing very fast with Earth robotics is because we can try and fail and try again, and the cost of trying is not so expensive, and there is a lot of available hardware. It's becomes a plug and play
Mhm.
problem and developing the algorithms. So it's very easy to find hardware. It's more difficult to develop algorithms, but you can always implement them in available hardware and get up in the morning, and in the evening you already have an operating robot, and it's quite amazing. Also, rapid prototyping enables us to develop very fast robotics.
Mhm.
It's still difficult to do good robotics, but you can try and you can improve.
Mhm.
So why are we not doing that well in space? So it's very expensive to launch, but not only that, we don't have good enough hardware and not available off-the-shelf hardware.
Mhm.
So with that understanding, we established Lulav 2 years ago, and we figured out that the most important part in any robotic mission are the sensors. And historically, what we used to use in space is those large radars or lidars, very heavy and expensive equipment that were designed specifically for a mission. If you look at the Apollo missions, they built this amazing radar, two types of radars, and they were very successful. But they were so heavy, and we could never use them in a small scale mission. So what can we do which is not so heavy and not so expensive, and we can use it in various types of missions? That's vision-based systems, using cameras in space. And with that understanding, we founded Lulav to provide better sensors for robotics in space. And that's a challenge, because we have cameras in space, but the computation systems, the computers
On Earth, yeah.
On Earth is advanced, but computers for space are like a decade or two behind in performance. So anything you can run on your PC or on any robotics computer board and is extremely powerful today, it's not available for space. It won't operate long enough. Maybe it will fail after a few days or weeks, but eventually, for deep space missions especially, you cannot rely on this type of hardware. And the hardware that is available in space is extremely low performance. And the question is how you can apply advanced computer vision algorithms on this low performance hardware, and that's what we're solving. So we are able to run high performance computations on relatively low performance radiation hardened computers, and then we can provide any robotic mission with an off-the-shelf solution which is easily modified for various application, lunar landing, on-orbit servicing, docking, rendezvous, all of these types of robotic missions in space.
Wonderful. So we're talking basically about vision-based navigation systems that are better in, again, performance than the LiDAR and radar that currently are existing, and also are much more cost-effective in terms of having less weight and just being smaller overall, right? You don't have to, you save the payload, mass, and you also save generally the fuel that you need to launch it as well. So very, very efficient, right? So now if we're talking again more about that, right? So can you talk about how does your vision-based navigation system just from all phases of the mission, right? If we start from launch, to orbit to the lunar surface, so how does that work throughout the process? If you can guide us through that.
Yeah. So after separating from the launch vehicle, you start a long journey to the moon. For example, iSpace, it took them a few months. It could be shortened to a few weeks or a few days, depending how much you can pay for the launch. And then what you need to do during that time is orbit determination. As you cruise through space, you want to know exactly where you are with respect to Earth or the moon, so you can do some orbit correction maneuvers. And traditionally, that has been done with transponders, radio transponders from Earth, and that's an expensive way of doing orbit determination. It works, but it's not autonomous. It's done usually on Earth and not on the spacecraft. And we can do it on board with a camera and estimate the orbit of the spacecraft while it's cruising anywhere between Earth and the moon. And that's the first part of the mission. So until you reach, for example, lunar orbit, and during a lunar orbit or Earth orbit, we can provide real-time orbit determination for the spacecraft, and that can be used to design and perform orbit correction maneuvers. So that solves this first phase of the mission. Then in lunar orbit, we can provide the actual position, velocity of the spacecraft, of the orbiter, with respect to the moon surface. And when it initiates the landing phase, we continuously provide them altitude, relative velocity with respect to the moon, and their position in the lunar frame. So they can navigate the lander to a specific landing site very accurately. So they can reach sub-kilometer accuracy, even less, depending on how much they want to put into the cameras, for example. It really depends on the type of camera you choose and the resolution you can obtain. And then the final phase, which is the most critical one, is vertical descent. So at perhaps you finish the braking phase at 1 or 2 kilometers, and then you orient the spacecraft to the vertical position and start descending. And during that descent, you need to know precisely your relative altitude, relative velocity with respect to where you're going to land. And also you want to map the surface and identify any hazardous objects, craters or boulders, and provide this information to the lander so it can make some small adjustments to the descent and land in a hazard-free site. And that we do continuously. At that point, we're using a stereo configuration, so we can have a very accurate 3D reconstruction of the landing site as we descend in real time. And that replaces scanning LiDAR, for example. So you can do everything basically from separation to touchdown with 2 cameras. That's quite unique, and a computing unit about 1 kilogram, and that's less than maybe 1/10 of the LiDAR system you can find today. So that's basically what we do. And for other missions, such as on-orbit servicing, so we will provide the relative orbit to the target satellite if you want to dock, or if you want to do a proximity operation. So you can obtain the relative orbit between the chasing satellite and the target satellite. And also if it's a docking, so you can provide the very accurate relative position, velocity at this final docking phase. So, and it's basically the same system. You just need to calibrate it and choose the right optics and cameras for the specific application. You can choose different cameras for lunar landing and different cameras for rendezvous or docking, but it's very flexible, and you don't need to change the actual hardware. And that's, I think, provides a lot of it makes the whole process, the whole system engineering process, much more easy for the designers of the mission, because they know what hardware they will use, and then they only need to adapt that. We provide them the algorithms, and they can optimize them for their specific application, because we provide them not only the sensor or the algorithm, we also provide them a simulated environment where they can run hundreds or thousands of simulations and scenarios and optimize the different parameters of the vision system for the specific application they want to do.
That's awesome. I mean, a lot of great applications, right, as we discussed. So for landing, and this we're going to discuss those obviously a bit later. So I want to just quickly emphasize on the on-orbit servicing applications, right? So this will be mounted on top of the spacecraft that will be docking or carrying out the, let's say, mission, right? So that will be completely different as opposed to the SSA, right? Space situational awareness providers, right? So that will be completely different from that, but those two will probably be complementary to each other, as I understand, right? Just to completely mitigate those risks of spacecraft operation just going wrong or just missing the target, right? So that's that's going to be very important, especially as we're looking now at the, some of the companies that are really now working on, again, providing those refueling services and
Right.
Orbit Fab and, many others also that are in the field. So I do see how they must and should be using, again, this.
That can reduce them a few years of developing some sensor suite for their applications. They can get this off-the-shelf sensor and relative navigation system, optimize it for their specific scenarios, and really save a lot of time. And it's a fraction of the size, weight, power, and cost of comparative radar or LiDAR systems. So it's an advantage in space relative to Earth, because the environment is quite controlled. You usually choose a time that you will approach a target. If it's lunar landing or on-orbit servicing, you control most of the parameters. You need the accuracy of a sensor to bring you to the performance you need, but you control most of the parameters, the time of approach, which angle you're going to approach. So for a vision system, it reduces a lot of the uncertainty compared to Earth, where you're navigating cars and some uncertainties can happen. Kids on bikes, dogs chasing cats, and all of those things we're familiar with from autonomous driving, which is a much more difficult challenge to succeed with vision on Earth. In space, the challenge is more running those high performance computations on a very low performance machine. That's
and especially if we're talking about, let's say, orbital debris, right? And removing those and tracking those. Some of those we just simply cannot track from Earth. Like it's just not possible to do that. And obviously we can track the families of those debris that are existing there, but we cannot fully track all of those based on their size. So I believe, again, that could be also very much applicable in that area as well.
Definitely.
Yeah, and I'm sure your team is approaching that as well from that side as well. So that's amazing. Now talking more about the again, back to the vision-based navigation systems, right? So with the surface of the moon, I mean, that's very important, again, very vital, but also it does not require any feedback or signal back from Earth, right, during this process. So that's also very important when we're talking about further missions, if we're talking about asteroid mining missions or missions like that. So maybe you can expand a bit more on how that will be, again, utilized for asteroid mining missions. How will that enable it? And, will it be also able, so it's mainly for navigation, will it still require any other type of sensors to identify let's say, the composition of the asteroids, and what part does artificial intelligence also can play together in again, partnership with your software and with your solution?
So what we are applying is what is known in the industry as simultaneously localization and mapping, or SLAM. That's the heart of the algorithm. And that's a geometrical optimization approach. It doesn't require prior information on the target. And so you can navigate in an unmapped area. It could be an asteroid, it can be on the moon. The moon is mapped, but it's not mapped to a resolution that you can use it for succeeding in a descent. Safely succeeding with prior information. And asteroids are generally unmapped. So with this approach, you can succeed in navigating with respect to an unmapped target. You can also combine it with prior knowledge on the structure of the target. If it's a lunar surface, you can match it to the digital terrain model and get your actual position in the lunar frame. You can identify the structure of a target satellite, or you can identify the structure of an asteroid. And then you can provide that information to some machine learning algorithms that will do perception. So you know your position in that frame and orientation in the frame of the target. Now you want to have some perception on what you're seeing, and those machine learning algorithms can then provide the robotic mission with insights of what are you seeing, and am I seeing a solar panel, am I seeing a thruster, am I seeing a docking bay, anything that is required to operate. And that's not part of our product, but it is supporting other parts of
It is the
those types.
Yeah. And if we're talking about artificial intelligence, Noam, so what will be, let's say, potential collaboration applications of that with your again service for asteroid mining or similar missions?
Yeah, so we generally see us as providing a coordinate frame for the mission, and then once you have a coordinate frame, you can do more in that frame, and what more you can do, that could be provided by AI models that can say, okay, this is what I'm looking for on this asteroid based on what we know and what we coded into our machine learning algorithms. That's the site we're looking for in the asteroid, and now you can attach the site to a coordinate frame provided by the navigation system. Similarly, for a target satellite, if you want to dock to a specific part of the debris or a specific part of a satellite, you can now know where to dock to, and you need to put it in the right coordinate frame. So that works together. Yeah.
Wonderful. So can you also just expand a bit more on the Lulav Space's Citros platform and how it manages to integrate all those multiple, again, robotic development tools and such as MATLAB and Simulink and Python? So maybe you can expand on that.
Yeah. So Citros we created to support our vision system in a way that it's validated enough for succeeding on the first time in a lunar landing mission. So it's not enough to have a good algorithm, and it's not enough to have even an implementation of the algorithm. It's not good enough to have hardware. You must have everything validated on a system level. You need to know in advance that everything will work to very high probability in the various scenarios you're expecting. And because we cannot test it on Earth, the exact scenarios for lunar landing, for example, we want to simulate it, and we want to provide the actual flight software and algorithms to inject the inputs of cameras, the inertial sensors, and any additional information simulated and simulated with various failure events and with various outlier measurements and various environment parameters. And we put all of that into Citros. Citros is a scenario machine. It enables you to run thousands and thousands of scenarios on the cloud and really see what the expected performance is and get a very good understanding of where you will succeed and where you will fail, and to do that very fast and do many design iterations compared to working a few years, getting to a design, launching, and then maybe succeeding or failing and going back to the design. Now you can do so many launches and crashes in a simulated environment and get all the information you need and get to a very high validation level. And that's what we're doing with Citros. And Citros is good not only for lunar landing, it's a more general robotics validation tool for any robotics software.
So as I understand it, it's not a two-in-one kind of package. So it's a separate service that also is complementary to the.
It's a separate service. We created it to validate our vision sensors, but ended up in a robotic software validation environment, which is a product on itself.
That's amazing. That's amazing. Okay, so now we can talk more a bit, about again the Lulav space itself, and your kind of internal structure, so in the team as well. So you mentioned a lot of your colleagues at the moment, they came together with you from the nonprofit that was working on the Beresheet, right?
A few of them, others came from other industries and academia in Israel. A highly experienced team. And today we are 12 people in the company working for the last 2 years. And we have 2 products, our vision system and Citros. So we're doing a lot with a very small team. And we are backed by VCs almost from day one, and quite successful in selling our products. Beresheet 2 mission, that's important, will take our vision sensors. That mission will include an orbiter and 2 lunar landers. And each of the landers will carry our landing sensor, our vision-based landing sensor. That will be our first space mission. And we are developing our sensors for that mission. And once we complete that, we are now ready to go to any other lunar landing or on-orbit servicing mission. So that's an exciting mission.
Very much exciting. And again, congrats to you again on successfully managing all those pieces. So you mentioned also that they came from different industries, your colleagues, right? So how did you approach, the hiring process? Did you so how did you find those individuals? Did they come from your personal network, from network of your colleagues, or you just happened to find them because you were searching for employees? So how did that go?
So some from personal network, and others just by approaching us and saying, okay, we want to take part in what you're doing, and realizing that they are talented and have the relative experience, they joined the team. And yeah, we were very, very lucky in with the people that joined us. And the team has background, because vision is not specifically for space, so vision navigation, the algorithms essentially are the same. So people have a lot of experience on Earth, and now the challenge is in adapting, developing, optimizing those algorithms for space applications, space hardware. And also,
no, sorry, go ahead.
And people who are familiar with robotics and simulation also find a very challenging mission here. So yeah, it's going well.
And I'm sure that again, that your solution is also like it has multi applications, right, in different industries out there. That's also played a big part, I'm sure, when it comes to the financing and VC support that you discussed, because we see all across the board a lot of companies really struggling to secure the funding, especially if they're doing technology demonstration missions, and but that again, your solution being again more applicable to also other applications, I'm sure that also plays a big part for that, right?
Yeah, it's doing space alone today, it's extremely challenging. And it's still it's an expanding market, but it's still small. Spacecraft are not flying to the moon every day. Maybe a few a year, that's a change, but there'll be dozens in the next decade. So we cannot rely only on that. On-orbit servicing is larger, so that's good. But because we were able to validate with Citros also Earth robotics, that puts us in a very good position with our products, which are both for Earth and for space applications.
And can you talk a bit more about like those for Earth applications again of your solutions?
Yeah, so on the simulation side, Citros can validate anything from a robotic vacuum cleaner to a lunar lander, because essentially a robot consists of a few software components, and it has the inputs from sensors, and it has output to thrusters or rudders or wheels, And that depends on the actual application. So on a software level, it's basically the same. And when you want to validate software, it's the same process that you should do, you should follow when validating a robotic vacuum cleaner or a lunar lander. Of course, for a lunar lander, you want to validate to a much higher level before actually flying it. And a robotic vacuum cleaner, you can validate to a very low level, then start doing actual experiments and then go back to the software. But in any case, it's really good and really saves time to validate as much as you can in simulation and not spend time with the actual hardware, because that's happens in real time, and with simulation you can run it 1,000 times in parallel. And also when you simulate, you can understand much more on what goes well and what goes wrong, because you can control the simulated environment. With an experiment, it's sometimes very difficult to understand what went wrong and what in their environment caused something to go well or wrong. So that's what people are realizing today, is that they should put much more effort into software simulation. And we are starting to provide a very good tool for that.
Very important. Very important. I agree with you on that. So, okay, so what is next? I mean, for Lulav Space, I mean, how does the time frames look like, and what is generally the next step, and how do you see again Lulav Space over the next 5 years or a decade? So, what is your vision?
Yeah. So, with our space sensors, we are planning to launch with the Beresheet 2 mission in 2025. So in about 2 years. And after that mission, that will put us in a leading position of providing validated sensors for space applications. Getting the heritage with the space system is very difficult, and anyone flying anything wants to use components that are already space qualified and have the heritage. You usually don't want to be the first trying out a new part of hardware or software in space. And we are planning that after the Beresheet 2 mission ends successfully, we will be in an excellent position of providing our software, our hardware to other missions. And we're not waiting until 2025. We're starting today. The lunar landing it's hard to find good sensors for lunar landing anyway. So companies are looking for alternatives to heavy radars or lidars. So they might take the risk with us the same way as SpaceL took, because they just don't have any alternative or cost-effective alternative. But after that, for on-orbit servicing and other missions, I think we will become a leading provider of sensors for space robotics. And CTROS will happen much sooner. By the end of this year, anyone developing robotics, it's a tool for developers. Anyone developing robotic software could use CTROS to validate their application and to try out different algorithms and try out different scenarios and compare it to what other teams are doing. And I think it will be a very popular tool between developers, and that's where we're aiming, and we want to contribute to the industry a very good tools that most people could be using even for free, and professional users, of course, could be using for some cost.
Okay, and let's say a company, let's say, wants to try out CTROS, for example, right now, because that you mentioned that's going to be the fastest one that you will be fully again developed, right? So they obviously reach out to you and they can pre-register for that, right, when it becomes available.
Yeah. So currently we have a few pilot customers that are using CTROS for Earth application and for space applications. And within 3 months, we will open up CTROS to early users, early birds, and they could be using it with the basic features. And by the end of this year, we'll have the full product available for anyone. So that's currently the plan. It's already working, and it's very useful to our pilot customers, and we hope it will be soon available for anyone.
Yep. So how do you approach, I mean, client, finding the clients, how do you approach that and just sales process if it's not a, secret information from your side?
No,
Yeah.
it's actually it's the most fun and challenging part of the
Okay.
work, because basically what we're telling teams developing robotics, we're saying you're developing, but you're not validating. You're validating only once you get to the hardware level. And sometimes it's a difficult understanding to say to someone, you're not doing your work good enough, or you can do much better. So we need to understand how to do our sales correctly, because people are doing exciting algorithms, and we're not saying you're doing anything bad with your algorithms, just you could validate them much better. So the question is, who are we selling to? We want to approach the developers sometimes, but we need to talk to their managers, the managers that are dictating the validation process. And that's something we're still studying.
Yep. Could be quite hard in this industry.
Yeah.
That just getting through the gatekeepers is sometimes very hard, right?
Yeah. Getting to the actual developers, it's not easy.
Yeah, which is very, I mean, not correct. I mean, in this industry, it's very slow. Just the sales process, just everything, communication. If you compare that to other industries, and that's not good to see, because it's really again hindering the growth of the industry and just the way things are approached.
Yeah.
But yeah, so generally, what tactics do you use? I mean, do you just call them, send them a cold email? Do you just go there and set an appointment, or do you just meet them at the events? Or what tactics do you use to
so we're starting to participate in more and more robotics events in Israel, and soon also in the US and Europe.
Okay.
And in those events, we just present what we do. We demonstrate the application. But we're also very lucky that there's a large network of robotics developers in Israel. So we can talk to them directly in the industry, in the academia. We know many of the leading robotics teams in Israel. So those were just talking to them directly, doing a demo, and then trying to move on to a pilot. And with some of them, we succeeded. And what we really want to do, once we are happy with the product, after the pilot phase, is to get to students in the engineering faculties, and we are sure that they'll be very excited to use this type of simulation tool to do their engineering projects, doing their even their homework tasks when they need to do simulation. And once they use it, they'll want to continue to use it when they come to the industry, because it's a very useful tool and very development oriented, developers oriented. So that's more of a bottom-up approach. On a higher level, once we can show managers that with Citros you can save sometimes years of development, you can do much more rapid and highly validated process. When they realize that, when we can show the value of this to their development process, so it will be much more, I think, it will be much easier to sell. Currently, we're saying it's good, and now we need to show them it actually is good on a commercial level.
Yep, and I'm sure you'll be successful in that. And obviously, myself and our team were keeping fingers crossed for you as well. So I'm sure all will be successful. And for again companies that are in the robotics field, or are looking again to use Lulav Space's services, you can just reach out to them directly at lulav.space, right? So your website, and that's not changing anytime soon, right?
No.
Yeah. Okay. So Lulav Space, that is. So yeah, make sure to do so. And yeah, any final notes or remarks, Noam, that you have? Now is the time to share it.
Oh, we're all looking forward to a few successful lunar landings in the next year. And I think that will really promote the entire robotics industry,
Perfect.
space industry.
Yeah, a lot of great projects ahead, right? So
Yeah.
everybody that's watching this, so again, stay tuned. A lot of great missions will be coming up. As Noam mentioned earlier, 3 companies are planning to do their launch this year, right? So obviously, will take some time until you are able to see that launch actually landing. But yeah, so make sure to stay tuned and also follow again our future episodes that will be coming out, and you'll hear a lot of great updates on those different missions as well, and many other space industry facts